Interestingly, standing here today, I've come more or less full circle here, because when I started looking at the psychology of human survival, a lot of my early work was done with shipwreck survivors. And I was looking at what was going on in people's behavior prior to the point of impact, during the point of impact or capsize, when people were in the water, when they were in the life raft, and what happened to a lesser extent afterwards. But I was particularly interested in the initial phases of people's responses. And my reason for that was that a lot of the behaviors we were observing that were happening for real is not the behaviors that we assumed that people went through when we were putting training courses together, not just for sea survival, but for land survival, both in the civilian world and in the military world. So I started looking at shipwreck because shipwrecks went on all the time. There are extreme survival conditions, and you could pick up a lot of the types of behavior that went on. And in '94, I put together a model. It was a psychodynamic model of people's behavior, and it broke down into the phases up there of pre-impact, impact, recoil, rescue phase, and a post-trauma phase. So we could see different changes in behaviors and different types of behaviors. And the one that particularly interested me was the question that we have of interest. There's a general interest in survivors and in survival. And what is it about certain people that enables them to survive horrendous circumstances? What is it about certain people who will carry on living when everyone else around them is dying? And that's what I was looking at that time. And after 2.5 years of looking into it, I got absolutely nowhere. And then I realized, and this was following another collision at sea and loss of life, that I've been asking the wrong question. The question I've been asking is, what makes a survivor? What makes them so special that they're able to survive? The question I should have been asking is, why do so many people die when there is no need for them to die? And this is right across the spectrum, not just dealing with sea survival, but with land survival, desert, jungle, Arctic, hostage survival, anything that puts people under duress. So, but the concentration here is to look at this, the psychodynamic approach there, and then having developed that, as Mike was saying, there's a lot of work has gone into this, a lot of experimental work. And what I was doing was to identify where the types of behavior, what the types of behavior were that we were witnessing, and how they tied in to the brain. And in 2012, we came up, after a number of experiments, with a revised model, same principles, but linking it with the cognitive system and the part of the brain that underpins the cognitive systems that were going wrong when people were under duress in a survival situation. And I'm going to go on to that in a short while, because the main part that we're concerned with here is the pre-impact phase and the impact phase. Okay, what happens beforehand and what happens at the point of impact, which in the case, the topic here is concerned with what happens when people go in the water, okay, behaviorally, but also the pre-impact phase. So what has happened to us before we go in the water, not just in the pre-impact phase, but let's go back a bit in prehistory. Because what you find is that we have adapted away from an aquatic environment. So the water is not an environmentally stable environment to us anymore. If you take most animals and mammals, you throw them in the water, they're generally quite happy in the water. Okay? We're the ones that have problems. A dog goes in the sea for a swim, the owner goes in to bring it out, it's the owner who dies. The dog comes out, shakes off, and walks off. Okay? Now there's one group of animals that have particular problems. Not these. So we've got horses and bears, pigs even, dogs, they're happy. But if you look at one particular group, hominoideas, and this includes the apes and ourselves. We all have problems here. Apes can't swim. Now, there's a little bit out there saying, well, yeah, there's a couple of apes that can swim, but they've been taught to swim. Monkeys can swim, but the apes can't. The apes will drown. And there's various reasons for this. One of them is bipedalism. Okay? We move around on 2 feet, so our plane of movement, our normal plane of movement, has changed quite dramatically. We're no longer on 4s, we're on 2 feet. And this has as problems. I came across the Journal of Human Evolution by, is that working? Have I got it? No. Hang on.
Just click on laser pointer.
That one?
Yep.
Lovely, thank you very much. Okay, so we've got bipedalism. And what Jan Wind notes, and this goes back 40 years, so we're picking this one up again, is that when most animals go in the water, they go in the same plane, more or less, that they move on land. Right? So their movement in the water is similar to on land. It's not the case with the apes, and that's partly because of this problem with bipedalism. Okay? But they're happy in it. You see the animals there, they're moving in the water more or less as they move on land. So there's very little change in their body structure. We can't do that. If you take a horse, horses are happy in the water. A horse will tread water. Right? Because it's gone in its normal plane of movement on the land. Now, we go in, we're bipedal, we have a problem. Okay? And the only way to get around that is to go into a horizontal system, which is not what we're known for. And if you look at the great apes, I did a quick check on this before I came out here. And in zoos, in recent years, these are the number of apes that have drowned in zoos in the Western world. Partly because apes tend to be in an open space, and they mark the space off by putting a moat around it, because apes do not like water. Monkeys do, so they keep monkeys in cages, because monkeys will swim. Okay? So that's one of the problems. Now, another difficulty we've got, and this actually ties into bipedalism, is that we've got a thing called encephalization. What do we mean by this? Well, if we take ourselves as primates, okay, we are apes. Now, what size of brain do we need to function quite happily as a primate, as an ape, out in the jungle, out in the savannah? Well, the brain size that we need is, and you can all do this, is about the size of your fist. Okay? That is the amount of brain tissue that you need to survive quite happily as an ape. Okay? Finding food, finding water, getting protection, finding a mate, fighting off the enemy, that's about the size you need. You don't need any more than that. But, as we know, we have an extra kilogram or so of brain tissue that we do not need to survive quite happily as an ape. And the difference between the tissue we need and the growth in excess luxury tissue is called encephalization. That is the process that goes with it. Now, what you find here is that to accommodate this excess of growth, because we've got a kilogram here, brain shape has changed from something like that, like a rugby ball in some things, to more a football sphere. So the front part and the back part have actually been pushed down. Now, a result of that is this thing. Okay, it's a nasopharynx. So what we've got in our case is that the nasopharynx, the nostrils, the part that you're breathing through, has been pushed down. The brain has pushed it down. And one of the reasons why we are bipedal is because of that extra kilogram of weight puts a lot of strain on the body, so by standing up, we're carrying it on top of the spine instead of having it dangling on the spine. So bipedalism and spurt in brain growth has gone hand in hand. But there's a trade-off, and the trade-off is your nostrils are pulled down. And as you can see on the lower one, back to Jan Wind again, by doing that, when you're in the water, you can't walk around on the bottom. You've got to be able to swim. You've now got to put your body into a horizontal position, the front and back, which is a lot of flexion, and that puts the nose underwater. So again, we are adapting away from the water aquatic environment as a stable environment, whereas most animals have their nostrils out of the water, so they've got a snorkel. Okay? So they're happy, they've got a snorkel, we don't, ours has been pushed in. We have something else that has adapted us away, locomotion. We've lost a natural component of locomotion in the water. It's called a tail. Okay? Tree shrews, monkeys, we don't have one anymore. Apes have lost tails. Monkeys have them, other animals have them, and it is a powerful tool of movement through the water. We don't have that anymore. So again, we're moving away. On the more behavioral side, the other thing that we've lost is the instinct of moving in the water. Animals have that. Most animals have that. You throw them in the water, they swim. They paddle around. They do doggy paddles. Horses tread water. They're happy in there. And it comes instinctively to them. We don't have that. Now, we compensate for that by using part of the brain that enables us to learn, and we learn how to swim in water. We learn how to float in water. But we've lost the instinctive part of it. So again, we're trading off here. So we're trading off the development of our brain against the aquatic environment as a natural environment because of these changes. Now, one of the things that we can do, particularly using this part of the brain here, the prefrontal cortex, which is about the third here, where we've got a major spurt in abnormal growth through our history, is that it enables us to think. So we are capable of thinking that we've moved away from an aquatic environment so we can make tools to aid us when we go back in to the aquatic environment. In other words, we can make life jackets, for example, buoyancy aids. We can do that. But we've not developed that part of the brain that suggests it's a good idea to wear the life jackets that have been developed with one part of the brain. Okay? And we see this sort of thing time and again. Okay. As I say, that sort of thing we see it time and again. Okay, that's just one example. So, how do you get people to wear life jackets when it doesn't occur to them to wear life jackets? Well, one suggestion is that you could make life jacket wearing an Olympic sport. Then it'll catch on, guaranteed. Right. Okay. On to the next part here, and getting more into the psychology of it. When I talk about psychology here, I'm looking at both the cognitive side and the general area of behavior. Okay, so what is going on? And looking at really at the point of impact. I'm not going to address the recoil period about how people live or how they die in life rafts or anything like that. Let's look at what happens when you get an impact phase. The part we're concerned with is the prefrontal cortex, because when I developed the psychodynamic model all that time back, one of the things that struck me was that all the behaviors that we were witnessing, all the dysfunctional behaviors, were all associated with the front part of the brain, the front third of the brain, the prefrontal cortex. So when we were running the experiments into this, we started to look at the areas, the cognitive functions that are supported by the prefrontal cortex and what is going on. And there's three main components here. There's a supervisory system, and that's basically this area here in blue, that's in the front. And that is responsible for your goals, your planning, high-level thinking, and importantly, what it does, it enables you to think in the future. So we have quite an extensive temporal span, which it does aid in survival in that it enables us to model situations in our head before they happen. So it's higher order thinking, cognitive function. It controls the other parts of the brain and develops plans and goals. The bottom one here, working memory, which is the orangey yellow bits, that is the part of the brain that does the online processing. Okay, so that is chugging over. It's a limited capacity system. So you get information in when you're doing your crossword, you're doing your Sudoku puzzles. It is the working memory component that is processing that information. The bit in the middle that you can't see because it's in between the two hemispheres is executive attention. And this links the supervisory system with working memory. And the supervisory system decides what you want to do. The executive attention then scours the environment for information that you need to support your goal or your plan. And importantly, it also has the job of inhibiting unwanted information from coming in. Okay, so you're not distracted. You can focus on the task that you need to do. It also gets information from long-term memory, puts it into working memory chugs over, temporal thing there, and then you have behavior. Behavior comes out. Okay, and that's the idea. So these are your three components within the prefrontal cortex. And what we've been doing over the years is just probing the function of these cognitive systems and how they interlink. And one of the areas that we've been working in is evacuation. Helicopter underwater escape training, which I know some people here will be familiar with. Put people in a simulated helicopter, dunk them in the water, turn them upside down, leave them strapped in their seat, and then we try to get them out. And then you also get the stage where you've got smoke, the wave machine, and you put the lights out. And that's great fun because a number of people, particularly the civilians that we get through there, some of them can't swim. The deepest water they've been in is their bath. Okay. Now this is useful because it is an opportunity for us legally and ethically to put the fear of God up people. So we are getting some interesting responses out of this. I have seen grown men vomit in a waste paper bin before they've gone in the helicopter underwater escape trainer. Okay, so that is so there's a lot riding on it. And as well as that, I don't know if you can see up here, there's a platform where people step off the platform. So it's evacuating from a ship, is the idea of it. So they're off the platform, straight in the water. So you've got the impact, you've got the immersion point there. Incidentally, this is at Fleetwood, the Nautical Training Centre in Lancashire, where we're using there. And I'll just introduce a colleague of mine in play here, Sarita Robinson. She was a PhD student of mine some time back. In fact, she was an undergraduate of mine some time back, and did her PhD in survival psychology under me, did a lot of work with helicopter underwater escape training. We've done a lot of collaboration in this area, and we've got a new study that we're setting up looking at the role of survival memory in water immersion and impact. We're working on that one at the moment. So that's Sarita. So what we've done, we looked at working memory, we took this and we probed it. And we had people going in the water, in the helicopter underwater escape trainer, but also we have people entering the water from the platform. And what we find is, and bear in mind, I'll say again, the working memory system in particular is a limited capacity system. The brain is an engineering device. Nothing magical about it, nothing metaphysical about it. It is a limited capacity signal processor. And it is limited in two ways. It's storage, working memory in particular. It can hold so much information and no more. And it's also limited in processing. So the speed of processing is fixed. You cannot go any faster than that. And part of it's fixed because of the speed of a nerve impulse. Brain trades off in different ways. It'll go into parallel systems rather than sequential, but you lose things. You lose control with parallel systems. With sequential systems, you've got control, but it's slow, it's sluggish, takes time. And what we found is that before the people went into the water, either through Hewitt or in the drop, immersion, we had no problem with a normal functioning of working memory. Drop them in the water, put them through the Hewitt. When they come out, we probe working memory again, and we find that you've got a restriction. So the amount of information that you can store is restricted. You've lost a lot. And the speed of processing has slowed down as well. So we find that. And what we've also done is we've probed working memory in other survival type situations and other situations of duress. We did some work with parachutists, both novices. We had novices, people just doing their first, second or third jump, and we had experienced people who've done more than 4,000 freefall jumps, competitor parachutists. And when I first did this study, my expectation was that the novices would have a severe restriction in working memory. This was from the other studies that we've been doing, indicated this, but that the experienced parachutists would have a slight, but possibly non-significant restriction. Wrong. What we found is that the novices and the experienced people, just prior to exiting the aircraft, when we probed, both had the same degree of impairment. Same level. What we noticed was the difference when they landed, because we tested them again when they landed, and we found that the experienced ones had shown full recovery. So working memory had bounced right back to full functional recovery when we tested them before they went up in the aircraft. The novices still had restricted working memory impairment for quite some time afterwards. It took them a much longer time for them to throw back. So what we're getting here is a basic system of impairment. Those who are trained, those who are experienced in the area, are marked out by their ability to bounce back and to recover. And this shows itself very much in life rafts. People who've done life raft training, have got experience in life rafts, their recovery rate, their behavioral, psychological recovery rate in a life raft is much quicker than those who have not. And we see it with people going through helicopter underwater escape training as well. So that's one of the things that, it works. So the training and the experience is not going to make any difference to you at that point of impact. When you fall in the water, that sudden fall in the water, you're going to get that restriction. It's how well you're trained that it copes with bringing back your memory. And we've also done it with firefighters, trainee firefighters who are going into their first major fire on the last phase of their training course. And we've done quite a lot on military work as well, which was part of my background there. And we're still doing some work with the SEER Combat Survival School down at RAF St Morgan. So we've got those coming up. Okay. Executive attention. We then probed executive attention, and I've looked at it in certain areas, not so much in water. We've done some studies in water, and we are getting the same effect, which is that there is an impairment in executive attention. It's a much slower effect. It takes a while to come in. It also takes a longer time to come out. So you're getting a restriction in attention as well. But this can go over 3 days. Quite often it's about a 3-day curve. So it's a slower thing. I say we have done it with helicopter underwater escape training. We've collected the data. We've not published it, but we have published in other areas on this one. Right. Unsupervisory system, the bit that is controlling it all, we have probed in Hewitt, and we have found impairment in certain areas. So the supervisory system is not a unitary function, which for a long time we thought it was. It isn't. There's actually 5 different but co-related functions going on, such as dual task coordination, search strategies for long-term memory, organising those, the planning and temporal span, your ability to plan ahead, not just to plan, but to plan ahead, internal monitoring of your own condition and the internal monitoring of what is going on in other parts of your brain, all the responsibility of the supervisory system, and the inhibition of prepotent responses. In other words, you're carrying out a behaviour. That behaviour is now maladaptive because the circumstances have changed. You're in the water. You've gone through the ice. So you have to stop that behaviour before you can introduce normal, correct behaviour. And that's where you get problems. And what we found is that there's no impairment in dual task performance. Search strategies in long-term memory, there's a question mark over that. Slightly technical one, which I'm not going to go into. We're not sure at the moment on that one. But we've got definite impairment in people's ability to plan and to think ahead. We've got impairment in internal monitoring, so your brain is not controlling the rest of the brain properly, and the inhibition of prepotent responses, which is why we get a lot of stereotypical behaviour that comes out. And one of the things that came out in Canada over there was people going through the ice in winter. So they're walking along the ice, they fall through the ice, and what do? Is they carry on. and they try and get out of the ice that they have been approaching. But of course, that tends to be weaker ice than the ice they've left behind them. So what the Canadians do is to train people, when they go in, to actually turn around and go back to the more sturdy ice than the flaky ice that they keep swimming towards, and it keeps breaking off when they try and pull themselves out. But that is their prepotent response. In another case, we had skidoos. So there was a skidoo who went through the ice, and a bloke was in the water. He had a partner with him on another skidoo. They're out. And he pulled his skidoo in and went to try and get this man out of the ice, out of the water. And he spent, as I recall, when he debriefed him afterwards, he spent about a good 20 minutes trying to get his grip and, excuse me, and couldn't get hold of him. And then he saw on the ground there were some trees, broken wood, branches. He got a branch, managed to get him out by using a branch. Okay, the bloke had been in the water for about 20 minutes. It was only later on when he, the rescuer, who was also having problems here, managed to recollect himself, that he realised that in his skidoo there was 20 feet of towing rope. And he didn't think about it. But he responded to what was on the ground. So it was an environmental trigger that he responded to. And that's what you do, you respond to environmental triggers. Something happens and you've not inhibited that behaviour. People getting out of buildings that are on fire. World Trade Center attack. Same things, you're going out the building, and as you're going out the building, you're leaving your office, there's smoke, the building is trembling, your phone rings. And people go back and answer the phone. It's an environmental trigger that you cannot inhibit. The brain's inhibiting function doesn't work. Okay, so that's what we're finding. So that's a short summary there, and I've got one more bit to cover. So what we're seeing generally, when you go in the water, you fall in the water, you're under ingest, what we see is a cognitive degradation in function, but not disintegration. So most of the brain, the two-thirds of it back here, and the subcortical parts, the older stuff, seems to carry on functioning. It's the front prefrontal cortex in ourselves that is actually degrading in function. Okay. And this baffled me for quite a long time. Why is it that the brain that does your thinking bit stops thinking when you find yourself in a survival situation? Surely that's the time you need it most. So I couldn't quite work this one out. But if we go back to the fact the brain's an engineering device, so if it's going to boost in one area, it has to trade off in another area. So this is one of the things where I say we're moving away from an aquatic environment as a stable environment for us, because we have got excessive growth in the prefrontal cortex, and we've had to compensate by that. We've traded off. This is what the brain's doing, and it took me a while to actually think this one through, but I came across a paper last year by Professor Amy Arnsten, published in Nature Neuroscience. And she runs a team at Yale University, and I've taken this slide from her paper. I'm sure she won't mind. But I borrowed it from her paper. And this actually helped to explain the question that was nagging me for quite a while. My approach has been the top-down approach. I say, right, I was intrigued by why people were dying when they shouldn't have died. There was no need for them to die. And they were dying at all different levels. So I went out and I looked at survival situations, debriefed survivors, identified the behaviours, put the behaviour together in a model, found the underlying neural structure for that, and then developed that. And was fascinated as to why it was this bit here, the front part of that was going wrong. I'd not seriously considered what was going on in the other two-thirds of the brain, because as far as I'm concerned, they seem to be working normally. So I didn't bother with it. Now, what we've got here is, I was to say that Professor Arnsten's area, she's not in survival, she's actually concerned with the role that chronic stress plays in neuropsychiatric disorder. So she's interested in neuropsychiatric disorder in the medical school. And she works from the bottom up. So she works at the biochemical level and the effect on individual nerves in the system. And what she was finding with the chronic stress is that if you boost the chronic stress, let's go over here, normally we've got the prefrontal cortex here, which controls your emotions, your actions, and your thoughts. and it's a normal function, okay? But if you have a condition which produces chronic stress, then the prefrontal cortex is taken offline, and that is what is happening. Under duress, you fall in the water, the prefrontal cortex is taken offline. Okay. But what she's noticed is that in the chronic stress conditions, you get boosts in neurotransmitters, and particularly in dopamine, adrenaline, and noradrenaline. There's a surge in the brain of those three. There's others as well, but those are the main three. And what she's found at the biochemical level is that they have two effects. On the prefrontal cortex, they basically have the effect of blocking the action of the nerves in the prefrontal cortex. So we're taking the prefrontal cortex out of action. But it also has a parallel effect of boosting, turbocharging the other parts of the brain. So my thinking that what is going on in the other two-thirds of the brain and the basal structures in there was that they were carrying on as normal. Wasn't picking up any dysfunction in those areas. Wasn't quite correct. What she was finding is that there is actually a turbocharged area. So what is going on in the other parts of the brain is that it's doing more faster. But it is reactive. Now, what's the basic difference between these two parts of the brain, the prefrontal cortex and the rest of the brain? The main difference is that the prefrontal cortex enables us to think ahead and to plan and do higher order thinking. The rest of the brain is responsible for reacting to the environment. Okay, so it is a part that deals with our moment-to-moment function and behavior in the environment. The prefrontal cortex, which we've developed over millennia, enables future planning, enables higher order thinking, but it is slow. It's a luxury. Your normal thought, if you're going to have a proper thought, it takes 8 to 10 seconds. Below 8 seconds, you just react. Might just be multiple choice reaction, but you're doing proper cognitive thing, that's 8 to 10 seconds. If you're in the water, 8 to 10 seconds is a hell of a long time. Okay, especially if it's cold. So, we've got this slow luxury piece of kit up the front of our heads, which is suddenly of no use. All right, it's not helping us. The rest of the brain is responsible for the present. You're in the water, you're underwater. Okay? Your life at that present moment is under threat. So what are you going to do? You're going to turbocharge that because your brain's worked out that if you don't get through that present, you don't have a future. So why have all that energy and resources going into a slow, heavy, cumbersome system which is going to actually impair your survival capability? Okay, it's one of the trains. So that's what's going on. We have got dysfunction, and we're picking apart the dysfunction that's going on in the prefrontal cortex, but we're also finding, particularly with the work on the neuropsychiatry side, is that you're turbocharging the present bits. And the behavior that we are seeing in people in survival situations, including falling in the water, is a consequence of closing down the functions of our behavior in the prefrontal cortex and boosting the present ones, the reactive ones. And that makes a lot of sense. It gives us an understanding of the pattern of behavior that is coming out. And I think, yeah, this is the last one here. So, in summary, what we're saying here is that we have problems in the water because we've adapted away from the aquatic environment, both anatomically and behaviorally. We've actually adapted away from it. So we need to learn and adapt to get back into it. It's not an environmentally stable environment for us anymore. The immersion impact degrades higher order cognitive function, doesn't disintegrate function, it degrades it. But it boosts our immediate response and our reactive response. But those responses, because they're reactive and they work in the present, are triggered by environmental triggers. And we don't tend to have any control over that, or we've got limited control. And that is basically where we are at the moment on the survival side, psychology brackets. Okay, thank you. Thank you, everyone.